so far in the course what we've talked about is we've talked about differentiation. And we said, okay, what is differentiation about? The basic idea of differentiation is to say, how are things changing? And by understanding how things change, we see how we can get various applications. So things like related rates and optimization, these are very strong applications which come from understanding how things change. But there's other things we can do. So we want to move into the last part of the course. So we're going to have something new today. And at this point, you're probably saying, I've had enough of derivatives. I want to be done with derivatives. In fact, you might even say, at this point, I'm kind of anti-derivative. And so we're going to be talking about anti-derivatives going forward. And of course, when you hear the word anti-derivatives, you think of something like the following, where people are just like, yes, I too am against derivatives. No more derivatives. But that's not quite what anti-derivative actually means. So what are anti-derivatives? Well, so we say that if I have a function, I'll call it capital f of x. It's an antiderivative of little f of x. So I'm given little f. I want to find some function capital F, which has the following property. The derivative of the function I find is the function that I started with. So now it's not I'm trying to take the derivative of something, it's I'm trying to find something whose derivative is what I have. So let's go ahead and do a couple problems. So here's a list of functions. So these are the functions we're given. We want to find some new functions such that when I take the derivative of what's on the right-hand side, I get the left-hand side. So is there any function that we know whose derivative gives us e to the x? All right, you know that one. That's pretty good. All right. Right now it's just e to the x, because look, it says find antiderivatives. There we go. We'll get to the plus c in a second. All right. How about, is there some function whose derivative is 2x? X squared. All right, all right. All right, that's good. Is there some function whose derivative gives us cosine? Sine. Yes, we saw the sine. And it opened up our eyes. Now, is there some wonderful, amazing, beautiful function whose derivative gives us 1 over 1 plus x squared? Arctangent. Oh, what a beautiful, amazing function that must be. Okay, so there we go. So it's not so hard. Now, somebody said plus c, because it's certainly true that these are not the only antiderivatives that exist. So for example, if I went to the e to the x and I added 1, the derivative of e to the x plus 1 is still e to the x. So that says antiderivatives are not always unique. However, they're almost always unique in the following sense. So when I have an antiderivative, any other antiderivative differs up to a constant. And the reason we know that is this is something we proved using the mean value theorem. You know, we proved it, we might as well use it. So if I have an antiderivative and my function is reasonably nice, then any other antiderivative is unique up to a plus c. Now, I won't define what reasonably nice means. I'll just wait and surprise you in Calc 2, because then it'll be fun. All right, so that tells us that we can go through now and actually update and say, if I have e to the x, the antiderivatives have the form e to the x plus c. Antiderivative of 2x is x squared plus the constant. Antiderivative of cosine of x is sine x plus the constant. And antiderivative of 1 over 1 plus x squared is arctangent of x plus the constant. Now, when do you need a constant? It's when you're finding antiderivatives. And if you are asked to find an antiderivative and you forget the plus c, you'll lose a point. And we don't want to lose any points. So we're just going to get the habit of when we're finding antiderivatives, we're going to toss in the plus c. Now, how do you actually handle the plus c? Well, occasionally what you do is you have additional information. You might say, I'm looking for an antiderivative with a special property. And so that gives you information, and that information helps you solve the plus c. And we'll see an application that does that. Now, in terms of notation, we have notation for derivatives. That was the d over dx. Now, we're going to introduce new notation for antiderivatives. And so what you have is you have this long thing here. And if you look at this, what does it look like? It's like you took an S and you sort of started stretching it out. Put it on the rack and just start, because that's what this is. It's a long S. It's a very big S. And we'll understand why we want the S in the next couple of days, why the S is there. So whenever you see this, we call this the integral f of x dx. It really stands for find the antiderivative. Because sometimes the antiderivative is referred to as the indefinite integral. Now you might be thinking, ooh, is there a definite integral? Well, we'll get to that as well. But that's not a topic for today. All right. Well, at this point, you're probably thinking, it took us a long time to find rules for derivatives. We're probably going to spend a lot of time finding rules for antiderivatives. And the answer is no. Because derivatives and antiderivatives are really two parts of the same coin. So instead, we're just going to put up one slide and sort of stress about this for the next 5 minutes. So this looks like a ton of information. But if you look at this closely, what we've done is we've listed two things. In the bluish font color is a rule for a derivative. In the reddish colors says, hey, what does this become for antiderivatives? So what we're taking is all our knowledge for derivatives and saying, what happens when we go to antiderivatives? Now there's a couple of things that we should point out automatically. The first one here. This says that antiderivatives are nice when it comes to addition and scalars. Another way to say that is antiderivatives are linear. So if I'm looking for antiderivatives, I can break up the problem whenever I see addition. I can pull constants out when I see constants out in front. Now, there's another special case, which is down here, which says that if I want to take the derivative of some function, capital F, of kx, by the chain rule, oh my gosh, there's a typo here. This should be a capital F here. Sorry about that. No, wait, that's correct. That should be a lowercase f. Oh, phew. I was worried. I was getting old. Okay, but by the chain rule, a k comes out in front, which says if you ever integrate some function with a kx on the inside, you divide by k. Now, this is a special case of the chain rule. I should warn you that this is a really, really special case of the chain rule, and that what you think might be true for the chain rule going forward is not going to be as easy as you think. We're actually going to spend a couple of days talking about what happens to the chain rule. So we talked about integrals are linear. The chain rule is coming later on. Or the product rule, oh, that's so good, we're going to save that for Calc 2. It's good stuff, what the product rule becomes. But now we say, okay, we have a set of functions whose derivatives we know. And so, for instance, we talked about some of them. The derivative of sine gives us cosine. So the antiderivative of cosine is positive sine. And we do this for all the trig functions. That gives us, what is it, 1, 2, 3, 4, 5? Oh, well, 4 here. Derivative of cosine is negative sine. Now, this is the one that always throws people off. So the integral of sine is negative cosine. So you have that sort of like reverse behavior. When you're talking derivative of sine, you get positive cosine. You're taking antiderivative of sine, you get negative cosine. So be careful. If I take the derivative of tangent, I get secant squared. Antiderivative of secant squared is tangent. Derivative of secant is secant times tangent. The antiderivative of secant times tangent is secant. So there's not a lot of surprises here. And we've already done the arctangent. Oh, what a great function. Derivative of log x is 1 over x. The integral of 1 over x is log x, of course, plus c. We've done the e to the x. The integral of e to the x is e to the x plus c. This is an important one. We use this one a lot. We know that the derivative of x to the power k is kx to the power k minus 1. So the antiderivative of x to the k is x to the power k plus 1 divided by k plus 1 plus c. So now instead of bringing the power down and subtracting 1, now you add 1 to the power and then you bring the power all the way down to the denominator. Now, at this point, if you were to do a count, you'll see that there are 8 antiderivatives that we have listed here. There are 10 total antiderivatives that get you from Calc 1 to Calc 3, which means that this list is not very long. It's a very, very short list of things that you need to know the antiderivative of. We'll add the other 2 by the end of the semester. That we'll save for later on. All right, any questions about our basic rules? There should be no surprises. What used to be rules for derivatives, now rules for antiderivatives. Okay. So, let's try some problems. All right. So find the antiderivative of e to the x plus 1 quantity squared dx. Now, let's do this by the way you're not supposed to do this. Because a lot of people will do the following. They'll say, hey, I feel like I should do some sort of reverse chain rule. And they say, all right, well, if I were thinking about it like a reverse kind of chain rule kind of deal, I have something squared. What's the integral of something squared? It would be something cubed. And then you would divide it by, in front, 1/3. But then you're like, oh, but I got to remember to account for the derivative of the inside. So what's the derivative of the inside? E to the x. So there are a lot of people who will write this down, including me. I'll write this down. Do you think it's true? I did write it down. I don't often write stuff down that's false. Now, in case you're wondering, what does this turn out to be? I will say, I mean, it's not very exciting to do this, but this is 1/3 times e to the 2x plus e to the x plus 1, and then plus 1/3 e to the minus x. And of course, you're saying, Steve, of course this can't be right. You forgot your plus c, so I'll just throw on a plus c. What do you think? True or false? All right, so I will tell you this is false. It doesn't work. Now, at this point, you're probably saying, really? It feels so good, though. Why doesn't it work? Now, the reason that this will fail is actually not so bad. It's not so hard to see what's going on that causes you trouble. So, suppose you were to take the derivative of this expression. So, the derivative of 1/3 e to the x plus 1 cubed, and I'm going to write this divided by e to the x as e to the negative x. If you were to take the derivative of this, what you would get is the derivative of the first term, which is 1/3 times 3 times e to the x plus 1 to the power 2, because the 3 comes down, subtract 1. The inside stays the same. Then what comes next? The derivative of the inside, and then there's still that e to the minus x. And this one you're saying, look, Steve, it's success, because those cancel, and those cancel, and I wanted e to the x plus 1 squared, but what's left? Plus, there's other stuff. 1/3 e to the x plus 1 quantity cubed times the derivative of e to the negative x, which is, whoops, I almost have enough space here, minus e to the minus x. And this part matches, but this does not. So this is why it's not just as simple as, oh, I can divide through by the derivative of what's on the inside. So unfortunately, that will not work. So please don't do it. All right. So what will work? Well, the problem is we're not really going to be able to integrate e to the x plus 1 quantity squared as written. But here's the cool thing that we're allowed to do. We're allowed to use algebra or trig identities, should we have trigonometry, to rewrite our expressions. So what's something we can do with e to the x plus 1 quantity squared? I'll give you a hint. There's a square there. So we can square it. We can FOIL, expand. So when I'm asked what's the antiderivative, or if you like, the integral of e to the x plus 1 squared, I can say, well, that's the same as doing e to the 2x plus 2e to the x plus 1, because I can expand it out. Now what we can do is go through, and we can do them sort of a piece at a time. And we can do it in any order we want. For example, the reason we can do it in any order we want is because it's addition. And addition says I can handle each piece individually. So let's start with some pieces which are probably easier. How about the plus 1? That'll become x. So there's going to be a plus x. How about 2 times e to the x? Now, does the 2 make a difference? No, the 2 will still be there. It'll still be a 2. So I just have to figure out what happens to e to the x. What's the antiderivative of e to the x? E to the x. So there's still a 2 e to the x. So the antiderivative of e to the x is e to the x, and 2 comes along. How about the antiderivative of e to the 2x? Yeah, so this is where this rule comes in handy. See, because it's basically saying the 2's on the inside, I'm going to divide by 2 the answer. So normally the antiderivative of e to the x is e to the x, but because it's 2x, I'll divide by 2. So it's e to the 2x over 2. Now, for full credit, what do we add? Plus c. And that is the correct answer. And you can even check and say, look, these don't match. They're not even close. So you got to be careful. Be careful. Do the work. All right, well, let's try another one. Find the antiderivative of secant theta plus tangent theta squared d theta. All right. Well, first thing you should always ask is this one of my 8 that I know? And unfortunately, no. Secant theta plus tangent theta squared doesn't show up. Okay, so it's not one of the 8 that we know, so what do we do? Now, if it's not something you know, you say, let me see if I can rewrite it to something that I do know. All right, so we can, again, it's a technique, it worked before, should it work again? If we expand this, we'll get secant squared theta, then we'll get the cross terms, 2 secant theta tangent theta, and then we're going to get tangent squared theta on the end. And that's all d theta. Okay, so far so good. Now let's just sort of check. All right, secant squared. Let's see. Oh, there it is. We can do that one. Secant squared is good. It's on our list. How about secant tangent? Let's see. Is that on our list? Yeah, that's right there. Secant tangent. That's good. We can do that one. How about tangent squared? It is not on our list. So what can we do for tangent squared if it's not on our list? We can, sorry, what? Rewrite it. Oh, I like that idea. See, one of the things to remember is whenever you have trigonometry, there's always a trig identity. Unfortunately, it might not be the one you need because there's like a million trig identities. But there's only 6 that you need to carry you from Calc 1 to Calc 3. And you probably know those 6 by heart, but I'll mention 2 of them right now. Cosine squared plus sine squared. Do you remember this one? What does that equal? Yeah, good. All right. Well, it turns out there's 3 ways to rewrite this expression. And the other way you should know is imagine dividing everything by cosine squared. So if you divide cosine squared by cosine squared, 1. Sine squared over cosine squared, what's that? Tangent squared. 1 over cosine squared, secant squared. Now what this allows you to do is it says I'm allowed to replace something that has a secant squared with something which has a tangent squared. I'm also allowed to replace something that has a tangent squared to something with a secant squared. Now we like secant squared. It's on our list of things we know the antiderivatives for. So our goal is to get rid of the tangent squared. So we're going to replace this tangent squared by secant squared minus 1. Now, if we do that, we can say, okay, using our identities, there's a secant squared and another secant squared, so we get 2 secant squared. We have 2 secant times tangent. And then we don't forget about the minus 1. So now we go through and say, all right, what's the integral of secant squared? What's the integral? Antiderivative. tangent. And don't forget the 2. So 2 times tangent, theta. Antiderivative, secant times tangent. It's secant. And then don't forget the 2. So 2 secant. Antiderivative of minus 1. Is it minus x or is it minus theta? Theta. Now how do we know? The answer is, look at what you're integrating with respect to. You're integrating with respect to theta. Theta is your variable. All right, and for full points, plus c. And there we go. All right. So this is going to become somewhat of a very common running theme that we have. Let's take what we have, the problem that's given to us, and let's work to rewrite it into pieces that we can understand. All right. Well, let's try another one. Okay. Find the integral of 27x cubed plus the square root of x cubed plus 2x to the 6 all over x to the 4th dx. That looks a little different. What can we do? Okay, so notice we have addition up in our numerator. Whenever you have addition upstairs in your numerator, that says I can separate the terms out. So I can rewrite this as really 3 things being added together. So this becomes the antiderivative, 27x cubed divided by x to the 4th plus the square root of x cubed. Let's write this in a calculus way. What's another way to write the square root of x cubed? 3 halves. X to the 3 halves divided by x to the 4th. And then 2x to the 6th, divide that by x to the 4th. All right, so we're using our basic algebra. What's another way to say 27x cubed divided by x to the 4th? Yeah, so there you can cancel a bunch of x's, so you're left with 1x downstairs. So I'm going to write this as, you can write it as 27 over x. I'm going to write it as 27 times 1 over x. Just to say the constant doesn't matter, I'm going to keep the constant to the side. X to the 3 halves divided by x to the 4th. What will that become? It's going to be x to some power. Okay, so you take 3 halves, subtract 4, and you get 5 halves? Is that right? Oh, negative 5 halves. Yeah, right. Because you make 3 halves minus 4. It's like 3 halves minus 8 halves. So negative 5 halves. Okay, how about this last one? 2x squared. All right, we probably should have started with that one. Dx. Okay, so now we go through them one at a time. Now you'll notice I left the 1 over x as 1 over x. I didn't write it as x to negative 1. Now the reason that I chose to do that is because if you go back to the rules, you'll see that you have kind of 2 rules that involve powers of x. When it's simply 1 over x, that's done a little differently. So 1 over x becomes log x. Because the rule up here won't apply. If you think about it, suppose k were negative 1. If you have x to the negative 1 power, what does it say to do? Well, it would say you take x to the 0 divided by 0. But if it's one thing we've learned in our class is we don't want to get close to a division by 0. So we're going to avoid that. All right, so let's work through it. So the first part, the first term, what does this become? 27 natural log x. This next term, what do we do? Well, so negative 5 halves is our k. So k is negative 5 halves. We need to add 1. So if I take negative 5 halves, add 1, what does that get to? Negative 3 halves. So that's the new power. So x to negative 3 halves. But now we have to also divide by our new power. So we need to divide by negative 3 halves. Now if you divide by negative 3 halves, take the reciprocal, it's like negative 2/3. Okay, now we come to our last one. So the 2, that's fine. Antiderivative of x squared. add 1, and then multiply by 1 over the new power, so 1/3. X cubed, and plus c. Don't forget your plus c. And you should always have it, even though, don't wait till the very end to include it. Include it from the start. Why? Because we will pay attention. And we pick up on these things. So I'm just doing a little bit of rewriting, not much. Plus a negative 2/3 is just the same as minus 2/3, and 2 times 1/3 is 2/3. And there's our answer. All right, good. So far, we're probably feeling pretty good. Like, okay, it can't be that bad. It can't be that bad. All right. Well, here's the thing you should know. It's bad. It's really, really bad. All right. So differentiation is easy in retrospect. And may not feel that way, and I don't want to trivialize it. I don't want to say it's trivial, but when I say it's easy is there's a list of about a dozen things you need to know. And if you know those dozen things and you can apply them, which comes with practice, then any function I hand to you, you can run through the machinery. It might take half a page like some of the problems on the exam, but you can do it. So taking derivatives becomes somewhat mechanical in some sense. It's just a matter of know the rules and apply them. The problem is antiderivatives, it's really, really tough. So I've written down an integral, which doesn't seem that exotic. All I did was I took this one and I flipped it over. It's a function, and if I were to ask you to take the derivative of this one, it'd be just about as hard as taking the derivative of that one. But here's the thing. This antiderivative was very easy. This antiderivative, when I say no one knows, I literally mean nobody knows. Wolfram Alpha won't touch it. Mathematica, forget about it. They can't do it. So there are integrals which are not hard functions which we cannot find the answers for. Now be careful. When I say we cannot find the answers for, it doesn't mean that they don't exist. It just means that there's no nice way to find the expression. Because there's sort of the theory, and then there's the practice. In the theory, if you have a nice function, and by nice I'll tell you what I mean continuous. That's enough. There's other things you can throw in as well. If you have a nice function, it has an antiderivative. Actually finding it can be very, very challenging. So be careful here. I'd like to say that integration really becomes more of an art. So that's what I say here. It's an art. I don't know why I'd say hard. I think that's implied. I probably should say they're fun. Then people are like, oh yeah, that means they're hard. All right. So how do you do it? Well, the answer is it's a lot of practice. But basically at the end of the day, and even after you go through Calc 2, what it's going to boil down to is that you have a collection of about a dozen rules, and of which we've already talked about roughly 10 of them. So maybe there's 14 rules. And all you need to do is know how to use those rules. And whenever we do antiderivatives, that's what we're going to come back to. It's really mostly comes down to saying, how do you rewrite the expression in terms of things you can do? So a lot of calculus becomes about algebraic manipulation, trig identities, rewriting expressions, being careful with your arithmetic, which is why we stress so much those ideas. It's because that's what's going to be able to let you do these things. All right. Now, let's try another problem. Okay. So, let's talk about acceleration. We have a particle, which at time t, the acceleration is given by the following expression. Acceleration is 6t minus sine of t. The location of the particle at time 0 is 7, and the location of the particle at time 1 is 12. And the question is, where is the particle at any given time? So I'm told how the particle is accelerating. I'm told where it's at 2 particular times, and I want to find where is the particle at any generic time. Now, we should pause here and think about, we've done problems involving acceleration before, but they were different. The kind of problems that we talked about with acceleration in the past were, here's a position, get to acceleration. So if we start with position, how do we get to acceleration? We took derivatives. In fact, we took derivatives twice. Now we're going to go backwards. Now we're saying here's acceleration. We want to get to position. So how are we going to get from acceleration back to position? We're going to take antiderivatives or integrals twice. So we're going to build up to it. All right, so let's start. So we have our acceleration is 6t minus sine of t. So if I want to get to velocity, that's the antiderivative of acceleration. So I can mark doing the antiderivative in the following way. So let's take the antiderivative of 6t minus sine of t. Do we know the antiderivative of 6 times t? Well, the 6 is a constant. How do you take the antiderivative of t? I can think of it as t to the 1 power. So the rule is add 1 to the power, so it becomes t to what power? T squared, divided by the new power, so 1/2 in front. Antiderivative of sine. What's the antiderivative of sine? Negative cosine. So I can think of it as minus negative cosine t. Of course, we'll clean that up in a second. And then what? Plus c. So there's a constant that comes when we take an antiderivative. So that's what velocity looks like for some constant c. Now, of course, we can clean this up. This is 3 times t squared plus cosine of t plus my constant c. Am I able to solve for c now? So the question is, am I able to solve for c comes down to saying, is there something I know about velocity? Because if I know something about velocity, that oftentimes helps me solve for what c should be. Unfortunately, we don't have any information about our velocity, so we can't solve for c. But that's okay, we'll move on. So now we go into our next phase. Okay, so we're after our position. So how do we get from velocity to position? Yeah, we're looking for the indefinite integral, or if you like, the antiderivative of velocity. So we're trying to look for 3t squared plus cosine of t plus c dt. Now you might be saying, am I allowed to integrate plus c? And the answer is, sure, why not? C is some constant number. I don't know what it is, but it's some constant. So what I'm going to do is I'm going to treat it like a constant. And then we can integrate. So let's go through it term by term. Okay, so we have the integral of 3 times t squared. Well, the 3 is 3. How do you integrate t squared? We add 1 to the exponent, t cubed, and then over 3. So 1/3 t cubed. Antiderivative of cosine, t? Sine t. All right. Antiderivative of plus c. It'll be plus c times t. All right. Plus, what else do we need? Well, we already have c, so we choose another symbol. So in this case, it doesn't really matter what symbol we choose, but oftentimes you work your way through the alphabet. So we'd have now 2 constants we don't know. We don't know what c is, we don't know what d is. Okay, so now we need 2 pieces of information in order for us to simplify this. So let's see what we do know. Well, we're told that we have information about location at time 0 is 7. So that statement, the location at time 0 is 7, is shorthand for saying s of 0 equals 7. So let's plug in 0 into here. If I plug 0 into this expression, what do we get? Well, you get 0 and 0 and 0 and d. So this tells us that d equals 7. So now I can update. So I can update and say now s of t, that's t cubed plus sine of t plus c times t plus 7. Now what's my other piece of information I know? time at 1 is 12. So if I plug in 1, I get 12. The time at 1 is 12. All right. So let's plug in 1. When we plug in 1, we get 1 plus sine of 1. And sine of 1, we can write that as sine of 1. Good. Oops, sine of 1. All right. Can't simplify that. Plus, well, t is 1, so c plus 7 equals 12. So I can subtract the 1, I can subtract the 7, and I can also subtract the sine of 1. So we get that c, well, 12 minus 8 will be 4 minus sine of 1. So, updating, we get that s of t is t cubed plus sine of t plus 4 minus sine of 1 times t plus 7. And there you go. Life is good.